This is an AQA A-level chemistry topic. It's from year 13 and it's structure determination. This is part 3. In the first parts we looked at carbon-13 NMR and introduced proton NMR. We're now going to continue with proton NMR, looking at some of the additional details and also then look at some of the sort of things that may come up in an exam. Please do have a go at the activities. You then get to know what's going well and what might need more attention. So let's begin with the first activity. We're looking at interpreting NMR spectra, following on from what was in the last video really. So what do we know from here? Well, we've got two peaks because we can see them here, and that means we've got two hydrogen environments. And you can also see that I've got a peak here between 9 and 10, which tells us that we are dealing with an aldehyde group. I've also got 3 peaks in one environment. It's around 2.1, and we can see that that fits within this range where the H is on a C next to a C double bond O. It fits with the integration trace. I've got 3 in one environment, 1 in another, and from there I can deduce that this is ethanol. So a lot of information that we can take on board that will actually get us a long way. But there is more that we can do. Let's look at that same spectrum again, but now let's look at it in high resolution. For a high resolution spectrum, it's essentially like you're looking at it through a telescope. You're seeing it really up close. And the difference is what we see here. So what are the key differences? Well, you can see that there are still the 2 peaks in the same areas, but the peaks have split, this one into 4, and this is split into 2. So what does that actually tell us? Well, actually, a great deal. So high resolution NMR spectrometry. This is something you will be needing to analyse, and it's important that you take on board the information in this blue box. When we get the splitting, it's caused by the presence of neighbouring non-equivalent hydrogen atoms. What that means is, if I look at a hydrogen and I see the carbon it's bonded to, I go to the neighbouring carbons and I count up how many hydrogens are on those carbons, but where their environment is different to what we're seeing in the one that we're actually investigating. Once we know how many of those there are, we've got the neighbouring, we've checked that they're not in the same environment. However many that number is, we add 1, and that's what our peak will split into. So it might split into a doublet, a triplet, or a quartet. It could go further. Got doublet, triplet, quartet, pentet, sextet, septet, etc. So let's look at what we can actually do with this. Why would it be a quartet and a doublet within this species? We've got the structure there, so let's start highlighting. I've got 1 H in this environment. The H is yellow, and I'm going to look at how many neighbouring non-equivalent hydrogens there are. Well, I go to my carbon, I go next door, and I can see I've got 3 hydrogens there. They're in a different environment to my H. So I take my 3 neighbouring hydrogens, I add 1 to that, which gives me a number 4, and that means that the H in this environment, the H on the COH, is going to be a quartet. If I then go back to look at the other 3, I take 1 of my H's, all 3 of those are in the same environment, I look next door, and there is 1 neighbouring hydrogen. So I take my 1, I add 1 because it's the n+1 rule, and that tells me that that would give rise to a doublet. So have a read through this and answer the question. So here we're looking at how many peaks are there going to be. Well, we know there are 3 peaks. We're going to look at which of those peaks relates to which hydrogen environment. So I'm going to colour code again, and you can see my colour coding. I've got 3 yellow, 2 green and 1 purple. If I then start to break that down a little more, I can look at the chemical shifts, and I can see I've got a peak just above 10. Now that tells me I've got an RCOOH group, my H on the carboxylic acid, and that relates to what I see here in purple. I can also see there's only 1 hydrogen in that environment because my integration trace is 1 to 2 to 3. So it's a singlet. That's the other important thing. So we know it has no neighbouring non non-equivalent hydrogen atoms. Let's move on and look at another peak. We've got the peak here at about 1.1, so that fits in the 0.7 to 1.2 range. That tells me we've got an RCH3 group, and we've got 3 hydrogens in that environment. It's also split into a triplet, and that triplet means that it's got 2 neighbouring non-equivalent hydrogen atoms. Well, actually we can see this. I go to my H's, the yellow that I'm talking about, and I can see that if I go next door, I've got 1, 2 of the green hydrogens. Different environment. 2 plus 1 is 3, hence a triplet. Finally, I go to my third, where I've got a peak at 2.1 to 2.6. It's got an integration trace of 2 hydrogens in that environment, and it's a quartet because it has 3 neighbouring non-equivalent hydrogens. Taking this through, looking at the integration trace, I've already touched on this, but the integration trace shows us we've got a 3, a 2, a 1, and the colour coding shows which one relates to where. So there's lots of different ways that we can attack this information and analyse this information. So let's move on. We're talking here about solvents. This is not to be confused with tetramethylsilane. Tetramethylsilane is our reference, but CCl4 or CdCl3 is the solvent we use to dissolve our samples in. Why are they useful as solvents? Well, what's absolutely at the heart of this is that there are no hydrogen environments. D is essentially deuterium. It's a heavy hydrogen, and it's got an even number of nucleons. And from the background that you will have read about on this, for NMR to work, you need to be able to get nucleon spin. And that only happens when there's an odd number of nucleons. Okay, let's move on and do a little bit of a summary here. So we can see my 3 hydrogens in yellow. I've got an integration trace of 3 and an integration trace of 3, so that could be either of those peaks. I've got 2 hydrogens in one environment. That means that I can really show that my 2 is going to be this peak that we can see at about 4.1. It's the only one that has 2 hydrogens in the environment. And finally, we've got our final 3 peaks. But which of these is going to be which for the 3 hydrogens? Well, the yellow is going to be the singlet, and we know that because there are no neighbouring non-equivalents. The carbon next door is bonded to a double bond O, no hydrogens. I know my blue because of the integration trace, as I've said, and that leaves the green. Now, the green, 3, integration trace 3, and it's a triplet. And it's next to a C with 2 H's. You count the H's, you add 1, that gives you what it splits to, we get the triplet. Going to talk a little bit as well about what you find when you have a quartet and a triplet, because it's often an indicator that there is an ethyl group. That's a good shortcut to look for when you're trying to put together structures in exam questions. A quartet and a triplet, you should be thinking along the lines of there being an ethyl group within that structure. So let's go on to look at some questions now. Have a go and then we'll review. First thing to watch out for here, just so you don't fall at the first hurdle, we're asked for branched chain alkenes, C5H10. So I could have 2-methyl-but-1-ene, I could have 2-methyl-but-2-ene, or I could have 3-methyl-but-1-ene. Once I've got all of those, I can think about what my structures will be when I've added Br2 across the double bonds. So we're essentially looking here at electrophilic addition mechanisms, good bit of crossover, but we would end up with these 3. And I'm going to go through and highlight the different environments now. So I can see in the first one, I've got 1, 2, 3, 4 environments. In the second, I've got 1, 2, 3 environments. And in the third, I've got 1, 2, 3, 4 environments again. So once I've got all of that, I'm asked about the one that's got 3 peaks, so that's 3 environments. It's the middle one. So once I've got that, I can highlight which ones I'm talking about. You might also do that with chemical shift values from the NMR if they're provided. But if I look at the integration traces, I've got 6 in the first environment, highlighted yellow, 1 in the second environment, highlighted blue, and 3 in the third environment, highlighted pink. And what would their splitting be? Well, my 6 H's are all in carbons bonded to a carbon with no H's. So 0 plus 1 is 1, it's a singlet. The pink, I've got one neighbouring non-equivalent on the next door carbon, so that's going to be a doublet because it's 1 plus 1. If I go to this hydrogen, the blue one, I've got 3 non-equivalents to the right of me and 3 non-equivalents to the left. That's 6 in total. 6 plus 1 takes us to a splitting of 7, and there we would get a septet. Another question for you to try. So on this one, we have got esters, molecular formula C5H10O2. What's important to note here is that we're dealing with 2 singlets in E. So 2 singlets means that we're trying to find as many hydrogens in one environment as possible. So let's start off with what we can do. We know that it contains an ester group. That's what we're told in the question. If I am then thinking about what I can put in that will give me lots of hydrogens in the same environment, I'm going to think of multiple methyls. And you can now see that we have added 3, 6, 9 hydrogens all in an identical environment. The difficulty is that we can't get an ester with the hydrogens on that side, so we need to rethink it. So I've now got my 9 on the other side, and that leaves me with 1 hydrogen which I can slot in here, and you can now see that I have generated an ester. I've got 1 hydrogen in one environment, and I've got 3, 6, 9 in a second. I've got 2 peaks. For the second one, I've already touched on this earlier in the video. 2 quartets and 2 triplets. So immediately that should be flagging up that this may well be ethyl groups. So let's give that a go. And I've added an ethyl group on either side. Now you can see that we have got 1 environment, we've got a second environment, but more than that, we can look at the splitting. My green hydrogens have got 3 neighbouring non-equivalents, so their peak will be a quartet. My yellow hydrogens have got 2 neighbouring non-equivalents, so we've got a triplet. We've got 1 quartet and 1 triplet. If I go to the other side, I have 2 hydrogens in this environment with 3 neighbouring non-equivalents. There's my second quartet. And if I go to my final 3 hydrogens, they have got 2 neighbouring non-equivalents, so that makes them a triplet. Here's another question for you to try. See how you do. So I've brought the table over so that we can work out what it is that we want to be able to work out, and we're looking at a peak at 2.18. It's a singlet and it's got 3 H's in the environment that we're dealing with. So what we're looking at here is immediately I'm going to go to the 2.18 is between 2.1 and 2.6. So we are going to have somewhere in our structure a COCH3 group. Now, if I then go to the singlet peak at 3.33, that also has 3 hydrogens in the environment. Now, it's C5H10O2, so it's certainly not going to be the haloalkane. So for the 3.33, we're really dealing with this. And we have got an R, O, C, H, and whichever other bits. We've got 2 pieces of the jigsaw here. And it then gets not more complicated, but we're not so worried about the positions of the peaks on the next one, because I've spoken previously about a quartet and a triplet making you think of an ethyl group. If you are highlighted to go towards 2 triplets, then you might be thinking about a CH2 in the middle. And then from there, with my 3 pieces of the jigsaw, I need to be able to put together my overall structure. I can take a look at what I've got up at the top, and I'm going to switch the top one around with my CH3COO. Now I know that those 3 H's are going to be a singlet because there are no hydrogens on the second carbon. From the second carbon, I'm going to add my CH2 and my CH2. It makes sense that that's going to follow because both of those are triplets, and it also means that I know that they're not influenced by neighbours on the other side. That then allows me to go to my final piece of the jigsaw, and I add this in, taking us to the answer that you can see here. Another question for you to try here. Multiple choice. So this also ties in with a huge amount of other content potentially. So butan-2-ol and acidified potassium dichromate is going to take us to butan-al. So I put my butanal in. I've got my hydrogens drawn in so that I can count up, and I can actually see that I've got 1, 2, 3, 4 different hydrogen environments. If I move on to ethanoyl chloride and methanol, my ethanoyl chloride is going to yield the ethanoate ion, and my methanol, I end up with my CH3 on this side. And you can see I've got one environment here and I've got a second environment over here. So the correct answer on this is actually B. Now you can go through and prove the correct answers are not C and D. I'm not going to do that for you, but it's good practice if you wanted to try. Another question for you. And again, this is relying on you working out what the different environments are. So I've got one environment here. I've got a second environment. I've got a third environment. I've got a fourth environment, and I've got a fifth environment there. So there is no symmetry there. There are lots of them. On the next one, I've got 1, I've got 2, I've got 3, I've got 4, I've got 5, and I've got 6. If I move on again, you can see that I've got 1 here, I've got another 1 here, and another, and another, and another, missed one in the middle, and another, and finally 1 here. So I've got 1, 2, 3, 4, 5, 6, 7 peaks. So let's count those up so far. I've got 5, I've got 6, and I've got 7. If I go on to the other side, I have got my CH3 and my OH. Now there's no symmetry here, so I am going to have an H coming off each of the 5 components. So I'm going to put those in, and you can see that I've got 1, 2, 3, 4, 5, 6, 7 once again. And finally, I go to here. I've still got a peak, an H coming off here, and then here, and then here, and then here, and then here. 1, 2, 3, 4, 5, 6. Correct answer is therefore P, because it only has 5. And final question to end this video. U and V are other isomers of PQ, RS and T. U consists of 2 singlets. V is a cyclic alcohol that exists as optical isomers. So let's take a look at how we can tackle this. Now, once again, what I want here is symmetry. I want to get as many hydrogens in one environment for U. So I'm actually going to start with a CH3, 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 all coming off the same carbon. What have I got left? I've got another 2 carbons, I've got another 3 hydrogens, and I've got 1 oxygen. Well, let's put in a C double bond O and a CH3. I have got 1, 2 environments, and it's C6H12O. When it comes to the optical isomer, I'm going to recommend you start with a carbon in the center, and you're going to build your tetrahedral structure because you want it to be an asymmetric carbon. Now, the first thing I'm going to put in is the smallest possible thing that I can put in, and that's an H. And that's because that gives me more to play with, more to think about, and more to reconfigure as I go through. I also know it's an alcohol, so I'm going to put my OH on. And once I've done those, I'm going to think, what else can I put on that is small? Something that there's not going to be, that there's going to leave me a lot left with to make the cyclic component of this structure. So my next obvious choice is going to be CH3. Now that leaves me with 4 carbons, which I'm going to put in to a cyclic ring. And if I put my H's on there, you can see that I've got 7 on there. I've got 3 and 1 and 1. I've got my 12. I've got my oxygen. I've got my 6 carbons. And most importantly, I've got my asymmetric carbon center. So quite a lot to unpack there. I am going to recommend that the best way to get your head around structure determination is to go through this and then start to look more and more at past paper questions that really do add a level of challenge. And it's only practice that helps you get past that. For now though, thank you for listening and goodbye.